Welcome to The Explainer. Today we're talking about motion, but not in a boring textbook way. We're going to turn it into a visual story. You'll see how a simple line on a graph can tell you everything about a journey, from a quick jog around the block all the way to a planet zipping through space.
All right, let's just jump right in with a question that sounds super simple, but it's actually kind of deep. Right now, as you're sitting there, are the walls of your room moving?
Well, the answer is yes and no. It totally depends on your point of view. See, to someone standing on the street, your room is perfectly still. But what if we zoom out, way out, to an astronaut looking down from space? You, your room, everything. You're all hurtling through the cosmos on this giant rock we call Earth. So motion is always relative. It's all about your frame of reference.
So, if we're going to tell the story of a journey, any journey, really, from a road trip to a planet's orbit, we've got to learn the language first, the basic vocabulary. Okay, first up, we have two words that people mix up all the time: distance and displacement. They sound similar, but they're worlds apart. Think of it like this. Distance is the total reading on your car's odometer for a trip, every single mile you drove. Displacement? That's just the, as the crow flies, straight line from where you started to where you ended up. Much simpler. So let's put some numbers on it. Imagine you drive 60 kilometers to a friend's house. Then you turn around and drive 35 kilometers back towards home. The distance you've covered is the whole shebang. That's 60 plus 35, a total of 95 kilometers.
But your displacement? Well, how far are you actually from your starting point? You're only 25 kilometers away, right? That's your displacement. See the difference?
And this is where it gets really interesting, kind of like a brain teaser. You can run a full lap on a 400-meter track. You've definitely covered a distance of 400 meters. You're sweating, you're tired, but because you ended up exactly where you started, your displacement is a big, fat zero. Isn't that wild? This exact same idea applies to speed and velocity. Speed is easy. It's just a number on your speedometer, how fast you're going. But velocity? Velocity is speed with a direction. It tells the whole story. So just like with the running track, you could be driving around town at high speeds, but if you end up back in your driveway, your average velocity for the whole trip is zero. Okay, so now that we have the words down, let's get to the pictures. We're going to look at our first storytelling tool, the distance time graph. This is where we can literally see an object's entire journey unfold. So imagine something is moving at a perfectly steady speed, like a car on cruise control. On a distance time graph, its story is just a nice, clean, straight line slanting upwards. Super predictable, super constant. What that line is really showing us is that for every second that passes, that's the line on the bottom, the object covers the exact same amount of distance, that's the line going up. It's the perfect picture of steady, consistent motion. But what about the steepness of that line? The slope. What does that actually tell us? Does it mean anything? Oh, it means everything. The slope is the speed. Simple as that. A really steep line, that object is moving fast. A gentler slope, it's going slower. And if the line is completely flat, horizontal, well, that means time is passing, but distance isn't changing. The object has stopped, dead in its tracks. But, journeys aren't always so steady. What if there's a plot twist? What if our car slams on the accelerator? The story on the graph totally changes. The line starts to curve upwards, getting steeper and steeper. That curve is telling us the object is covering more and more ground every second. It's the visual signature of acceleration. All right, let's level up. We're going to switch out one of our main characters. Instead of plotting distance versus time, we're now going to plot velocity versus time. And trust me, this tells a whole different and honestly, a much richer story. Okay, now you got to be careful here. This is a classic trap. A flat horizontal line on this graph does not mean the object is stopped. Not at all. It means its velocity isn't changing. It's cruising along at a perfectly constant speed in a constant direction. In other words, zero acceleration. So if you look at this graph, the car's story is super simple. Steady as she goes. The line is just flat at 40 kilometers per hour. That car is on cruise control, no drama, no speeding up, no slowing down. But this graph has a hidden secret. That space underneath the line, it's not just empty space on a chart. If you calculate the area of that rectangle, height times width,
or in this case, velocity times time, you get the total distance the object traveled. It's this whole other layer of information hiding in plain sight.
And remember our car hitting the accelerator? What does that look like here? Well, if it's speeding up at a nice steady rate, its story on this graph is a straight line sloping upwards. The velocity is climbing and climbing. And the slope of this line, that tells you the acceleration, how quickly the velocity is changing. Okay, this table here is basically your cheat sheet. It puts everything side by side. Look at how a horizontal line means at rest on one graph, but constant velocity on the other. It's so important to know which story you're reading. Honestly, if you can master this table, you've basically learned how to read the language of motion. So these graphs are great for telling us what happened, but what's even cooler is that they give us the power to predict the future, to see where an object is going. And how do we do that? Well, all the patterns we've seen in our graphs can be boiled down to these three incredibly powerful equations. They connect all the key players: initial velocity, final velocity, acceleration, time, and distance. These are the ultimate mathematical tools for telling the story of motion. Think of these equations as shortcuts. They let you figure out exactly how fast something will be going or how far it will travel without ever needing to draw a graph. This is how physicists go from a visual idea to a precise mathematical prediction. So what's the big takeaway here? It's that by learning how to read a simple line on a graph, you've actually learned the fundamental language of the universe. I'm not kidding. The very same principles we use to track a car's acceleration are the exact same ones used to tell the story of a satellite whipping around the Earth or even a galaxy drifting through the cosmos. And that is an incredibly powerful story to know how to read.